Hi everyone, welcome back to the channel. My name is Priyansh Agarwal. In this video, I'm going to be covering 10 bitwise operator tricks that you must use as a competitive programmer. Before we get started, let me also tell you that when it comes to bitwise operations, they are very fast. If you compare it to addition or subtraction, they are a bit faster. But if you compare it to something like multiplication, division or modulo operators, then these bitwise operations are very fast. Okay, like they're just insanely fast. Now, one more thing that I want to say here is that you all must have seen on Code Forces or CodeChef. Generally, the trend is that 10 to the power 8 operations can run in 1 second, right? In C++ or sometimes in Java as well. But if you look at bitwise operations, you shouldn't be surprised if in some cases you are able to see even 10 to the power 9 bitwise operations running in just a second. So let's get started and let's look at the very first trick of this video. The first trick is to check if a number is an even number or an odd number. A very easy way to check if a number is even or odd is to do something like if x modulo 2 equals to 0, then you say that the number is even. Otherwise, you say that the number is odd, right? But what's the problem with this approach? The problem is that you're using the modulo operator. And like I said at the beginning of the video, the bitwise operators are much faster than multiplication, division or modulo operators. So what you can do instead is to check if the least significant bit in the binary representation of a number is 1 or not. For an example, if x is equal to 9, then the binary representation of 9 will look something like 1001. Clearly this bit, if you look at it, the least significant bit is 1. So this number is an odd number. Similarly, if x is, let's say, 10, then the binary representation of 10 will look something like 1010. And if you look at this bit, then this bit is 0. So this is a very cool way to check if a number is odd or even. You can just check if the least significant bit is 1 or 0. Right? A very cool way to check if the least significant bit is 1 or 0 is to simply do something like x and 1. What this will do is that it will take the AND of your number with just a single bit, which is 1, right? And if that number, if you take the AND and if it comes out to be 1, then you clearly know that the least significant bit is 1. So the number is odd. And if it comes out to be 0, then you know that the least significant bit is 0 and the number is even, right? So if you can look at these examples, x is equal to 9. Binary representation of 9 looks like 1001. 9 and 1 comes out to be 1. So this number is odd. Similarly, if x is equal to 6, the binary representation of 6 is 110. And 6 and 1 comes out to be 0. So this number is even, right? So this is one way to check. This is order of 1 and it is much faster than x modulo 2. Much faster than x modulo 2. So the second trick of this video is to check if a number is a power of 2. Again, this is very cool. When you look at a number which is a power of 2, let's suppose x is a power of 2, then how does a power of 2 look like in the binary representation? You would have something like this, right? 0, 0, 0 and 1 in the middle and then something like this, right? There will be just a single bit which will be 1 and rest all the bits will be 0. This is what means when you say x is a power of 2, right? Now, if you look at a number which is, let's say, x minus 1, then clearly just leaving this bit, as 0, all the rest of the bits towards the right will become 1, right? If you do x minus 1, this number would look something like this. Now do one thing, take the AND of these two numbers. Take the AND of these two numbers. And you will realize that the final AND comes out to be 0. Why? Because all the bits, there is no 1 and 1. Look at this one, there is a 0 corresponding to it. And look at all these ones, there are zeros corresponding to these ones, right? So you can check a number is a power of 2 by just doing simply x and x minus 1, right? If you want to look at another example where this does not hold and x is not a power of 2, you can take an example. Let's suppose x is equal to 10, right? Then the binary representation of 10 will look something like 1010. And now if you look at x minus 1, which comes out to be 9, then binary representation of 9 will come out to be 1001, right? If you take the AND of these two numbers, you will realize that you're getting 1000. Right? This is clearly not equal to 0. So 10 is not a power of 2. Okay. Now, how much time will this take to check if a number is a power of 2? Simply just order of 1. You're just doing x and x minus 1. And that will tell you if the number is a power of 2 or not. Right? There is just one problem with this approach, which is that it does not work for the case where x is equal to 0. Right? Because see, if x is equal to 0, then x is clearly not a power of 2. But when you do something like x and x minus 1, this number will still come out to be 0, right? So this is an edge case here. So what you can do instead is you can handle this case differently. You can say if x is equal to 0, then it is not a power of 2. Otherwise, I will check using this condition, x and x minus 1. Okay. And again, this entire stuff works in just order of 1. a very, templated stuff that you can use is to use this function, which can tell you if x is a power of 2 or not. Let's look at the third trick for this video. This is not entirely a trick, but this is a way in which you can play around with the kth bit. Okay. And if you look at the kth bit, what do I mean by that? Let's suppose x is represented in the binary representation like this. Okay. When I say kth bit, I am looking at the kth bit from the right. Okay. So this is the 0th bit. This is the first bit. This is the second bit. This is the third bit, 4th, 5th, 6th, and so on. Okay. These are the bits, how I am defining them. So when I'm talking about the kth bit, I mean the kth bit from the right, the kth least significant bit. Okay. Now, if I were to ask you, if you have to check whether the kth bit in a number is set or not, how will you check this? You can just simply do something like, if you want to check, let's suppose the third bit, if the third bit is set or not, you will just come here, you will put a 1 here, and rest all the numbers you will keep as 0. And then you will just take the AND of these two numbers. So if this bit is 1, what will you get as the result of taking the AND of these two numbers? You will get 1 here, and rest all of these numbers will be 0. Right? But just in case, if let's suppose this bit was not 1, what would happen in that case? Let's suppose, you want to find out, this was for the third bit. Let's suppose you want to find out the same thing for the second bit. Yeah. So if you look at the second bit, you will take the AND with 0, 0, 0, 0. There will be 0, 1, 0, 0. Okay. You want to take the AND of these two numbers. Again, I will repeat this x here. 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0. Now, if you take the AND of these two numbers, what will you get? You will get 0 at the end. So this clearly means if you want to check if the kth bit is set or not, you will just take the AND of the number with 2 to the power k, right? Setting the kth bit in the number and then taking the AND with it, correct? And if you get a number greater than 0, then you clearly know that there was a bit which was set, which is the kth bit. If the number comes out to be 0, then the kth bit was not set. So this is what you can do. Check if the kth bit is set or not by just doing something like this. Similarly, if you want to toggle, let's suppose, if you want to toggle the kth bit, okay. Let's suppose x is equal to this. Let's suppose you want to toggle this bit. What can you do? You can take a XOR with this number. If you take a XOR of these two numbers, what you will realize is that this particular bit will get toggled and rest all the bits will remain same. So you will get this. Okay. Similarly, if you want to look at another example, let's suppose you want to, toggle this bit. So you can take the XOR with 0, 0, 1, 0, 0, 0. And this number will come out to be 0, 0, 1, 1, 0, 1. Clearly, this bit has been toggled, right? So this is like taking XOR and toggling the kth bit. So this works like this. If you want to set the kth bit, okay, you want to say that I want to make the kth bit as 1. So what you can do is you can simply take the OR. Let's suppose x is equal to this. If you want to, let's suppose, set this bit. So you can take the OR of these two numbers, 0, 0, 1, 0, 0, 0. If you take the OR, this bit will become 1. Rest all the bits will remain the same. Okay. And similarly, if you want to, let's suppose, make this bit equal to 0. Okay. Let's suppose you want to make this bit to be 0. So what you can do is you can take an AND with this bit having 0 and rest all the bits having 1s. Okay, if you take the AND of these two numbers, you will clearly have this 1, 0, 0, and this bit will become 0 and rest all the bits will remain the same. Okay, so these are basically, some tricks in which you can play around with the kth bit. If you want to check if the kth bit is set or not, just use this x and 1 left shifted by k. If you want to toggle the kth bit, use XOR. If you want to set the kth bit, use OR. And if you want to unset the kth bit, take the AND with the NOT of 2 to the power k. Okay, look at it like this. So if 8 looks as something like 0, 0, 1, 0, 0, 0, then NOT of 8. Okay, NOT of 8 will look something like 1, 1, 0, 1, 1, 1, right? So if you take the NOT of a number, it just, toggles all the bits, right? So you can unset the kth bit by taking the AND with that particular bit being 0 and rest all the bits being 1. Let's move to the fourth trick of this video, which is to multiply a number or divide a number by 2 to the power k. Okay, let's look at an example. If let's suppose you want to say 10 divided by 2. So this becomes 5. right? Similarly, if you want to do something like 9 divided by 2, this becomes 4, right? What you can do is you can, right shift this entire number by 1 bit in this case. So if you look at binary representation of 10, binary representation of 10 looks something like 1010. If you shift this entire number by 1 step towards the right, what will happen? This will become 101, right? This bit will go away, this bit will go away, and rest all the bits will be shifted by 1 step towards the right, right? Clearly, this is 5. Similarly, if you want to look at binary representation of 9, it comes out to be 1001. Now, if you right shift this entire, binary representation by 1 step, you will remove this bit and rest all the bits will be copied towards the right. And this will be the number, which is 4, right? So if you have to divide a number by 2, you can do something like, if you want to divide x by 2, this is the same as saying x right shifted by 1 step. Okay, if you want to do something like x divided by 4, this is the same as saying x right shifted by 2 steps. If you want to do x divided by 8, you can do something x right shifted by 3 steps. Okay, so clearly if you want to do something like x divided by 2 to the power k, it is the same as saying x right shifted by k steps. Okay, so, and similarly, if you want to do x multiplied by 2 to the power k, this is the same as saying x, left shifted by k steps. If you want to look at an example, let's suppose, x is equal to 3 and you want to do 3 multiplied by 4. So this is the same as saying 3 left shifted by 2 steps. Okay, let's look at an example, or let's just consider this same thing. X is equal to 3. So the binary representation of 3 is 1, 1. Okay, now left shift this entire number by 2 steps. So 1, 1 left shifted by, this is binary obviously, by 2 steps, this comes out to be 1, 1, 0, 0. Basically, you shift the entire number 2 steps towards the left and you add zeros at the back of it. If you look at this number is clearly 12, right? 3 multiplied by 4 comes out to be 12. So that is how it works. So in order to divide a number by 2 to the power k, you will do something like x right shifted by k steps. And if in order to multiply a number by 2 to the power k, you will do x left shifted by k steps. Alright, let's look at the 5th trick of this video, which is to find out x modulo 2 to the power k. As an example, if let's suppose I tell you find out 10 modulo 4, this number would come out to be 2, right? So this is the same as saying x or 10 modulo 2 to the power 2, which comes out to be 2 in our case, right? So we want to find this efficiently, right? Again, without using the modulo operator. Why? Because the modulo operator is not that great, okay? So what you can do is you can do something like x and 2 to the power k minus 1. So let's look at an example for this. Let's suppose I tell you find out 10 modulo 2 to the power 2, which is the same as saying 10 modulo 4, right? So what I've given you in the formula, do x and 2 to the power k minus 1. So do 10 and 2 to the power 2 minus 1, which is the same as saying 10 and 3. Look at the binary representation of 10. It comes out to be 1, 0, 1, 0. Look at the binary representation of 3. It comes out to be 0, 0, 1, 1. You take the AND of these two numbers and you'll get 1, 0. Clearly, this is the binary representation of 2, right? And 10 modulo 4 is what? 10 modulo 4 is obviously 2. Now let's try to understand why this works, okay? So if you look at 2 to the power k, what happens when you look at 2 to the power k? It is like saying 1, 0, 0, 0, 0, 0, k times. Okay, these are k bits. These are in total k bits. When you look at something like 2 to the power k minus 1, then this bit becomes 0. Rest all the bits become 1. Okay. Now, if you take the AND of any number with this number, what will happen? If you take x and this number, what will happen? You will just look at the last k minus 1 bits and you will get that from x. So if x was, let's suppose, equal to 0, 0, 0, 1, 0, 0, something like this. If you take the AND with this number, what will happen? You will be taking the AND of these two numbers, right? If you take the AND, what will you get? You will just get the last k minus 1 bits of x, which are 1, right? So you will get, this number will come out to be something like 1, 0, 1, 1, 1, right? This is what you'll get. So this is the same as saying if you want to take x modulo 2 to the power k, right? If you want to take x modulo 2 to the power k, then if the binary representation of x is something like this, and if let's suppose 2 to the power k is this, okay, if this is what you're looking at, then look at this part of x. Look at this part of x. Can I say this part of x is already a multiple of 2 to the power k? This is 2 to the power k. This is 4 times 2 to the power k. This is 8 times 2 to the power k. This is 32 times 2 to the power k, right? So this entire part towards the left is already a multiple of 2 to the power k. Sorry, you are concerned about the bits towards the right of the kth bit, which are these bits, right? These bits are going to represent the remainder when you multiply, or sorry, when you divide x by 2 to the power k, right? So if you take the and, if you look at x, you have x, you have 2 to the power k, and if you take the x and 2 to the power k minus 1, this 2 to the power k minus 1 has all the k minus 1 bits towards the right as 1, right? They all are 1. So when you will take the and with x, this will give you all the bits which are towards the right of the kth bit and which are 1, right? So, and that will be the remainder when you divide x by 2 to the power k. Okay, so this is what you can do if you want to find out the remainder of x and basically, 2 to the power k, right? And this again works in just order of 1. This is much faster than the modulo operator. Let's look at the sixth trick for this video, which is to swap two numbers without using a temporary variable. So let's look at an example for this. Let's suppose x is equal to 2 and y is equal to 5. And I tell you to swap these two values. Okay, one way to do something like this is to have a temporary variable, and let's suppose this is z, and you can do something like z is equal to x, then you can do x is equal to y, and then you can do y is equal to z, right? What this will do is that it will swap the values between x and y. Okay, so now I want you to do the same thing without using a temporary variable, which is z. And how can you do this? You can do this using the XOR operator. So these are the three operations which you can do, and after these three operations, your x and y will get swapped. Let's try to understand why this works. So if I tell you make x is equal to x XOR y, so what will happen after this operation? After this operation, x will have the value x XOR y, and y will have the value y, right? Because we aren't changing y. After this operation, you do y is equal to x XOR y. What was your x now? Okay, your x had become x XOR y. So when you take the XOR of this x XOR y with y and y will get cancelled out and only x will remain. So this value, x XOR y will give you x. Okay, so now y has become what? Y has become x after this operation, while x continues to remain x XOR y. Then after this operation, do another thing, x is equal to x XOR y. So what was x? X was x XOR y. And what had your y become after the second operation? Your y had become x. So x XOR y, XOR x, x and x can get cancelled out. So your x becomes y. And your y had already become x. So this is how the values get swapped. If you were to look at this same example, let's try to see. X is equal to x is equal to initially x XOR y. So after this operation, x will become 2 XOR 5. What is 2 XOR 5? 2 XOR 5 is 7, and your y will continue to remain 5. Then you again do y is equal to x XOR y. So x will continue to remain the same, 7, while your y will become 7 XOR 5. What is 7 XOR 5? 7 XOR 5 is 2. Then after this operation, you do x is equal to x XOR y. So your x becomes what? Your x becomes 7 XOR 2. 7 XOR 2 is 5, and your y continues to remain 2, right? So in this way, you have basically swapped two variables without using a third variable, right? Okay, so the seventh trick is not really a trick, but it is a property which is very, very useful in a lot of CP problems. And it goes like this. If let's suppose I tell you that the number of set bits in A is equal to X, and the number of set bits in B is equal to Y, then the number of set bits in A XOR B, if it is equal to Z, then this condition holds. That Z is going to be even if X plus Y is even, and Z is going to be odd if X plus Y is odd. What do I mean by this? If the number of set bits in A plus the number of set bits in B, if this number comes out to be even, then the number of set bits in A XOR B will also be even, and otherwise this number will be odd. Okay, let's look at an example for this. Let's suppose I tell you X is equal to 5, or let's suppose if we are talking about A and B, let's say A is equal to 5 and B is equal to 3. Okay, so 5 has, you know, the binary representation as 101 and 3 has the binary representation as 011. Okay, now take the XOR of these two values. What will you get? The XOR of these two values will be 1, 1 and 0. Okay, so how many set bits did this number have? The set bits in this number were 2 and the set bits in this number were 2 as well. And if you look at the total number of set bits in these two numbers, it comes out to be 4, which is an even number. Okay, now look at the set bits in the binary representation of A XOR B. The number of set bits in the binary representation of A XOR B is equal to 2, okay, which is also even. So what I'm trying to say is that if this bit, let's suppose this is X and if this is Y, and if this is, let's suppose Z, let's suppose this is Z, then if X plus Y is even, then Z will be even. And if X plus Y is odd, then Z will be odd. Okay, you want to take another example? Let's look at this. Let's say A is equal to 6 and B is equal to something like, let's say, which has just one, let's suppose set bit. Let's suppose B is equal to 8. Okay, so binary representation of 6 is 100 and binary representation of 8 is 1000. Take the XOR of these two values and you will get 1, like the XOR of these two values will get 1110. Okay, how many set bits did this number have? This number had 2 set bits and this number had just 1 set bit. So total number of set bits were 3, right, which is a odd number. So clearly the number of set bits in A XOR B is also odd. Okay, let's try to understand why this works. Okay, if A has, let's suppose, these bits, okay, any bits, and if B has some bits, okay, it could be anything. Okay, if these are the bits in A and B, then if you look at it, let's suppose the total number of bits here are equal to X and the total number of bits here are equal to Y. What happens when you take the XOR of two numbers? Okay, let's suppose if there was no, collision, basically at any place there was no 1 and 1. What would happen in that case? Then in that case, the total number of set bits in A XOR B will be equal to X plus Y. Now let's suppose I tell you there is one bit which is same in A and B. What will happen to that bit? That bit will get cancelled out from both A and B. So how many total bits have you reduced from X plus Y? You have reduced -2. Let's suppose I told you that there were 2 bits which were same in A and B. What will happen in that case? You will reduce 2 more bits, right? See, if you look at this bit is same in A and B. So how many total bits get reduced from X plus Y? 2 bits get reduced from X plus Y. Similarly, if this bit and this bit is same, how many bits get reduced from X plus Y? 2 more bits get reduced from X plus Y. So clearly the number of bits that get removed from X plus Y will be how much? Will be of the form X plus Y minus 2 times K. K being the number of bits which are same in A and B. So clearly if you look at this number, then this number is going to be odd if X plus Y is odd and it is going to be even if X plus Y is even. Let's look at the 8th trick for this video, and this is a very cool trick, by the way. Let's suppose I tell you that X, this value can only be either let's suppose 10 or 5, and if right now the value is 10, toggle it to 5, and if the value right now is 5, then toggle it to, or change it to 10. If let's suppose this is what I want, let's suppose X can only have the value 10 and 5, then how will you do this? You will say if X equals to 10, then make it 5. Else if or X is equal to 5, then make X equal to 10. This is what you will do. A very cool way to handle the same thing is to do something like X is equal to 10 XOR 5 XOR X. What will happen in this case? In this case, if X was 5, then 5 and 5 will get cancelled out. If X was 10, then 10 and 10 will get cancelled out and 5 will remain, right? So in this way, you can make X to be equal to the second value if it is equal to the first value right now, and you can make it equal to the first value if it is equal to the second value right now, okay? So this same thing can be done in just one step like this, and this is a very cool way to do it. I've seen a lot of competitive programmers on Codeforces do this. So yeah, you can also do this. Okay, let's move to the 9th trick of this video, which is not exactly a trick, but again, 2 properties. Okay, so the first property goes like this, that A plus B is equal to A XOR B plus 2 times A and B. Let's suppose I tell you A is equal to something like 1001. Okay, so this number is 9, which can be written as 8 plus 1. Okay. And if I tell you b is, let's suppose, equal to 0, 1, 1. So let's suppose this is equal to 3 and it is also like 2 plus 1. Now tell me one thing, if you want to do a plus b, can I say it is the same as saying 8 plus 2 plus 2 times 1? Yes. And if you look at a XOR b, what will happen if you look at a XOR b? You will be doing 1 0 0 1 XOR 0 0 1 1. So the bits which are same will get cancelled out, but the bits which are not same will remain the same. So you will have the number as basically 1 0 1 0. So this is the same as saying 8 plus 2, right? So the bits which were not same in both of these two numbers, they have been added. But the bits which were same in both of these two numbers, they have been removed completely when you do a XOR b. So they have to be added twice. And now if you look at a and b, then a and b will be like saying 1 0 0 1 and 0 0 1 1. So this number comes out to be 0 0 0 1, right? But this 1, which is equal to 1, has to be added twice, right? So what you can do is you can simply say a plus b is equal to a XOR b, which will obtain all the bits which are not the same in a and b, plus 2 times a and b, which will obtain all the bits which are same in a and b, and it will add it twice, right? Similar is the second property. The second property goes like this, that you do a or b plus a and b, right? Same thing, if you have to look at a is equal to 9 and b is equal to 3, then you want to do something like 8 plus 1 and you want to do something like 2 plus 1, right? Now if you look at a or b will be like saying 1 0 0 1 or 0 0 1 1. So this number comes out to be 1 0 1 1, right? So this has 8 plus 2 plus 1, right? So it clearly has all the bits which were not same in a and b, and the bits which were same in a and b, it is adding them once, but they have to be added twice, right? So what you can do is you can obtain a and b after this. If you obtain a and b, this will be 1 0 0 1 and 0 0 1 1, which will come out to be 0 0 0 1, and then you can just do a plus 1 at the end, right? So this 8 plus 2 plus 1 and a plus 1. So that is why we say a plus b is equal to a or b plus a and b. Again, these two properties are very, very cool. They are useful sometimes when you're trying to find out two numbers, for example, having certain properties, right? So finally, let's move to the last trick of this video, which is only useful for C++ users. Again, sorry for the Java and Python folks. But yeah, in order to find out the number of set bits in a number X, how do you do it? Basically, you iterate over all the bits and then you count the number of set bits. That would result in order of log n total operations, right? But C++ has a very cool feature or a very cool inbuilt function, which is known as the built-in pop count. You pass in X to this built-in pop count function and it will return the number of set bits in X, right? This is very, very useful because this does this finding of number of set bits in just order of 1. This is not an order of log n approach. This is an order of 1 approach. Again, this is an inbuilt function. In case you're interested to find out how this works in order of 1, and if you're a Java or Python user and you want to replicate that same functionality, then sure, you can, Google it up and you can learn more about it. But for C++ users, if you want to find out the number of set bits in any number, stop using this, approach of iterating over all the bits. Just use this function, built-in pop count, and pass in X to it, and it will return the number of set bits in the number X. In case X is a long number, then don't use this built-in pop count. Instead, use built-in pop count LL. This is for long values, okay? So yeah, that was it for this video, guys. I hope you all liked it. I know this was a long video, but again, this would have been very, very insightful for people who are interested in bitwise operations. So now I'm very sure after this video, you will start to make use of these bitwise operators much more. In case you like this video, don't forget to smash the like button below. And in case you're new to this channel, we are about to bring a lot more content like this. So don't forget to subscribe. Another thing that I would ask you all to do is to comment out, the best trick that you found from this list of 10 tricks that I've covered. And in case you have any doubts about any of the tricks, be sure to comment down and I would love to help you all.